Problem number 4 on the study guide number 4. The problem that we're looking at here, where we're trying to maximize the area of this rectangle underneath this curve, and the parameters are the upper right corner of this rectangle has to be on the line x equals 2. And so we see x equals 2 right here. So just getting an idea what in the world is going on with this diagram is the key. And then we see that the rectangle right here has its upper left-hand corner on the curve 1 plus 2x, y equals 1 plus 2x. Slope is 2, the y-intercept is 1, so we have a 1 right there. And then, I don't know if I mentioned this or not, but the toughest part of this problem is in the setup of the problem. Okay, this is where students make the most mistakes. It just takes a little practice. You see a couple of these and you go, okay, got it. Notice that the height of the rectangle here is dependent upon x, and so x better be the x coordinate of this point right up here, but also it should be the left-hand side of this rectangle. So x represents the left-hand side of the rectangle, at least the x coordinate of the left-hand side. So the line x equals whatever this number is the left-hand side, and the line x equals 2 is the right-hand side. Okay, and so that makes the width of the rectangle 2 minus x. Okay, so that's probably the hardest part to see is actually labeling the width. And if you think about it, anytime you're having a hard time labeling something or solving a difficult problem, try to solve a simpler problem. Like, let's just say we have on our x-axis we have the number 1 there and we have the number 7 there. Okay, and 2, 3, 4, 5, 6, 7. And you wanted to come up with the distance between the 2 points. Okay, well, you can clearly see that the distance is 6. Okay, so to get from 1 to 7, you add 6. But if you wanted to express this length in terms of both of those numbers, you would express the length as the right-hand endpoint, 7, minus the left-hand endpoint, 1. So 7 minus 1 is how you're going to get that length. Okay, so we have the same situation going on here. The base of this rectangle has a length. If the right-hand endpoint has a value of 2 and the left-hand endpoint has a value of x, then the length of that base is 2 minus x. Okay, so that takes care of the length of the base, and hopefully by now you're already seeing that the height of the rectangle is a 1 plus 2x, because the y, meaning the height of the rectangle, is equal to 1 plus 2x. Okay, so then once we label our rectangle and we realize, oh, what we want to find is the area of the largest such rectangle, so we want the largest area. Alright, so we need to know, we need to rewrite or create a function, area, in terms of x. Alright, so area in terms of x is equal to the base of the rectangle, which again we said was 2 minus x. And we're going to multiply that base of the rectangle by the height of the rectangle. We already said that the height of the rectangle is 1 plus 2x. Okay, so now we have our area function. And we can go ahead and multiply using our FOIL method. 2 plus 4x minus x minus 2x squared. Okay, and if we want to rewrite that in terms of our largest power first, we get negative 2x squared plus 3x plus 2, concentrating along the way. And we have our area in terms of x, not factored, so it's easy to find the derivative, because we know that when we're trying to find a maximum value or a minimum value, we need to make sure we differentiate, set the derivative equal to 0 to find our critical points, and on and on and on, like we've done a million times now. So the derivative of a of x is negative 4x plus 3, and the derivative is equal to 0 when negative 4x plus 3 is equal to 0. Okay, in other words, when 3 is equal to 4x, and when x is equal to, be careful here, 3 over 4. So that's our critical point. It's our only critical point, and we can be really confident that at that critical point, that area is going to be a maximum. So I just had to pause the video. I had my daughter come in. I had to go say goodnight. And so I'm back. Not sure exactly what I was just saying, but let's do this. We just found the critical point, and that's when a prime is equal to 0. I'm confident that that's going to yield our maximum value, but let's make sure of that. Okay. We put 0 here and 2 here. X can't be less than 0. It can't be greater than 2. And when we put 3/4 here in the middle, we can pick a test value of 1, let's say 1/2. Okay, so 1/2 right there. And a prime at 1/2 would be, if we look over here at negative 4x plus 3. So a prime is negative 4x plus 3. So if we have negative 4 times 1/2 plus 3, that's going to be a positive number, right? Negative 4 times 1/2, that's negative 2. Negative 2 plus 3 is positive. Oops, I want it over there. Positive on that interval, and then let's say the number 1 over here in this interval, negative 4 times 1 is negative 4 plus 3 is negative. So just to confirm that negative on that interval, and so therefore we have a maximum value, right? So a is increasing until x is 3/4, and then a is decreasing after that. So therefore, we know we have a maximum value, and all we have to do is answer the question. What is the question? Find the area of the largest such rectangle. So the area then would be right here. Let's put it up here. Okay, so the area when x is equal to 3/4 is the 2 minus x, so 2 minus 3/4, and we're going to multiply that by 1 plus 2 times 3/4. 1 plus 2 times 3/4. Okay, well 2 minus 3/4 is 5/4, and 2 times 3/4, so 2 goes into 4 2 times, and we have 1 plus 3/2, and that's 2/2 plus 3/2, that's 5/2. So the maximum area of any rectangle with those limitations would be 25/8. 25/8. And 25/8 what? Anything? No, that's just 25/8. That's it.